Good morning. We're going to be filling in the back side of our Day 4 notes. Just a reminder that you can pause this video at any time to do calculations or to write information from the screen into your notes. You may want to pause the video right now to copy the equation for finding atomic mass into the box at the top of the back page of your number or Day 4 notes. If you guys remember, there are two numbers that they give us on the periodic table. We're going to look at the box for magnesium. The first number that they give us is called the atomic number. We should know what that number tells us. But they also give us a decimal number, a number that isn't a whole number, 24.050, I believe. That number is called the atomic mass. It is a decimal number because it is the weighted average of all of the isotopes of magnesium. And we're going to use the equation up above, right up here, to calculate these decimal numbers from the periodic table. One quick reminder that if you look at the percentages that they give us, the percentages have to be divided by 100 before they're put into the equation. And then AM stands for atomic mass of isotope 1, and then AM of isotope 2, of the two isotopes. All right, let's do an example problem. So this example is going to deal with chlorine. It says calculate the atomic mass of chlorine if the two common isotopes of chlorine have masses of 35.45 AMUs, and then they give us the percent abundance. There's 75% of that one. And then they tell us that the other mass is 37.29 AMUs, and there's 25% of that isotope. We're going to take that information, and we're going to plug it in with our knowns and unknowns, and then we'll plug it into the equation to solve for the decimal number, the atomic mass from the periodic table. So, the atomic mass of the first isotope was 35.45 AMUs. The percentage was 75.00%. And we do have to carry those two zeros along because those are significant figures. The atomic mass of the second isotope was 37.29 AMUs. The percentage of this was smaller. There's only 25.00% of that isotope. So all we need to do is substitute this information into the equation that we copied at the beginning of the period. This equation right here. So we are calculating the atomic mass of the isotope. That's the decimal number from the periodic table. And the equation tells us that we need to take the mass of the first isotope, which is 35.45 AMUs. We need to multiply that times the percentage. But we have to remember that that percentage needs to be divided by 100. So when you take 75.00 divided by 100, we get 0.7500. We do need those two zeros. You have to have them. They are significant figures. Now we're going to add that to the second atomic mass, 37.29 AMUs. And that has to be multiplied times the second percentage. But remember, we need to divide it by 100. So that would be 0.2500. Pause the video and replay it if this doesn't make sense. All right, the first thing we're going to do is we're going to multiply the two numbers that we need to multiply before we add. We also have to remember that there's a significant figures rule for multiplication. Here there are 4 significant figures. Here there are also 4 significant figures. So my answer needs to have 4 significant figures. I would definitely punch this into the calculator with me, but I'm going to give you the answer rounded to 4 significant figures. So 35.45 times 0.7500 gives me 26.5875. However, I only want 4 significant figures, so I'm going to round that to 26.59 AMUs. Got to carry my units along, okay? Now, I'm going to add that to the second mass times its percentage in decimal form. There are 4 significant figures here, and also 4 significant figures here, so my answer needs to have 4 significant figures. So 37.29, okay, times 0.2500, and I get 9.3225. But when I go to significant figures, I need 4. That's going to be 9.323 and AMUs. You have to carry your units along. Then the last thing that we do is we add those 2 atomic mass unit numbers together. That will give us the decimal number off of the periodic table, okay? Now, we have to remember that there's a rule for when you add numbers together, and it's different than the multiplication rule. We have to look right here. This first number goes out to the 100ths. It's precise to the 100ths. The second number measures all the way out to the thousandths. It's precise to the 1000ths. We have to remember that our answer has to be cut off at the least precise number, the crappiest measurement. So we have to round our answer to the hundredths once we get it. So I'm going to add those 2 numbers, 26.59 plus 9.323, and I get 35.913. But remember, our answer cannot go past the hundredths. So I'm going to cut that off as 35.91 AMUs. And that's the number that belongs on the periodic table. That is the atomic mass, or the weighted average, of those 2 isotopes. Hopefully that makes sense. All right, let's move on to another example. This one says, what if you don't have the percentage or the atomic mass? So the problem says, calculate the atomic mass of one of indium's isotopes. There are 2. If the atomic mass of indium is 114.8200 AMUs, that's the number from the periodic table, and one isotope of indium has a mass of 114.9041 AMUs and an abundance of 95.795%. So what we need to do is first we need to put in our knowns and unknowns, okay? Every problem starts the same way. They give us the actual number from the periodic table. They give us the atomic mass of indium. They tell us it's 114.8200 AMUs. They also give us the mass of one of the isotopes. They say that the first isotope has a mass of 114.9041 AMUs. They tell us that the percentage of that isotope is 95.795%. We don't know the second isotope. That's the one we're supposed to figure out. But we should be able to calculate the percentage. There's only 2 isotopes. Percentages always have to add up to 100. So if we take 100 minus the 95.795, that should give us the percentage of the second isotope. So when I take 100 minus 95.795, I end up with the number 4.205. Okay? That's the percentage of the second isotope. And then it's pretty easy to solve. All I need to do is to substitute all of this information into the equation to solve for atomic mass. Now here's the best part. We already have the atomic mass. We've got 114.8200, sorry, I need to rewrite that. 114.8200 AMUs. And that's going to equal our mass of the first isotope. Our mass of the first isotope is 114.9041 AMUs. And we're going to have to multiply that times the percentage of that isotope. But remember, percentages need to be divided by 100. So we're going to change that to 0.95795. Hopefully that makes a little bit of sense. Now, that's added to, okay? Remember, it's added to the amount of isotope 2, okay, the mass of isotope 2, which we don't know. I'm going to call that X. Multiplied times the percentage of isotope 2, but remember the percentage has to be divided by 100. When I divide that by 100, I'm going to get 0.04205. Hopefully that makes sense. So you guys, the best part about this is now all we're doing is we're solving for X. This is simple algebra. We should be able to do it. Do the things that you know how to do first. The first thing I would do is multiply these two numbers right here. This number has 3, 6, 7 sig figs. This has 2, 3, 4, 5 sig figs. My answer better have 5 sig figs. So I'm going to punch this in, 114.9041 times 0.95795, and I get 110.07. That's with sig figs. 110.07 in AMUs. Hopefully that makes sense. I've gotten rid of this. Okay? So you guys, here's the thing. I want to get X by itself. It's very easy to get this 110.07 off of this side if I subtract 110.07 AMUs from this side. That 110.07 disappears. But if you guys remember, if you do it to one side of an equation, you have to do it to the other. So I'm going to put here minus 110.07 in AMUs. Now, remember, when you do your subtraction, your answer can only be as good as your crappiest measurement. My answer better end at the 100ths, at the hundredths. So I'm going to take 114.8200 minus 110.07, and I get 4.75. That's awesome because that's already at the 100ths. So 4.75, and I'm going to write what I have left over here. So 4.75 AMUs, and then from the other side of the equation, I have equals X times 0.04205. Well, you guys, this isn't rocket science, but it is chemistry, which leads to rocket science, but it shouldn't be that difficult for us to solve for X. If you want to get X alone on the right-hand side, all we have to do is take this side and divide by 0.04205. That gets the 0.04205 off of that side. But remember, if we do it to one side, we've also got to do it to the other. And then the last thing is sig figs. There's 3 here. Here there are 4. I'm going to quickly do my math. 4.75 divided by 0.04205. And I get my answer with 3 significant figures as being 113 AMUs. That's the mass of the second isotope. Pause the video if you need to, redo the problem, but our work should look very similar no matter what problems we're doing.